Now we're continuing to talk about orbital hybridization. This is the second video. So we learned last class that some central atoms can have what we call expanded octets, which means more than 8 electrons around them. They can have more than an octet. Some can have 10, some can have 12. In order to explain this type of bonding, I think we had, well, for example, one of them was XeF4, which we drew in class, and we said that it had a lone pair here and a lone pair here, and then kind of like F, 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 F. I think we called that seesaw. So that has 1, 2, 4, 6, 8, 10, 12 electrons. To explain how all of these bonds can be equal, we need to use d orbitals when explaining our hybrids. So in this case, this S electron has promoted an electron to, and this is not explaining this one necessarily, to 1d, so you can have 1, 2, 3, 4, 5. So this would be 6. I really should have come up with an example for 5. So a better example of a molecule for the particular situation we're looking at would be PCl5, which has 10 electrons around the central atom. So in this case, the phosphorus, which has, this is its initial unexcited state, it would promote one of these s electrons up to a d orbital, giving it 5 possible places to bond. Then so that it wouldn't have 3 different types of bonds, these will hybridize. They'll make babies and we'll end up with still 5 bonds, but we'll call them sp3d. And we get this name from the things that contribute to it. 1s, 3 p's, 1d. Oh, here's the drawing. This is my drawing. Here it is down here. So if we use the d orbitals, we can either have 5 equivalent sp3d orbitals or 6 equivalent sp3d2 orbitals. sp3d2. The little numbers should be superscripts. So this page should match what you have on that big geometry sheet that I gave you. It's just written a little bit differently. For the family, the geometry family that is linear, that family, you're going to be using sp hybrid orbitals. They would be made from 1s and 1p in the central, around the central atom. These are some examples. They'll be linear. If you have a trigonal planar geometry, that will be created with 3 sp2 orbitals. Each one around the central atom would be an sp2. They would have been made from the central atom contributing 1s and 2p orbitals. Here are some examples. Everything in the tetrahedral family will be using sp3 hybrids, whether it's tetrahedral or if it's these, even if these are lone pairs, and this is bent. If electrons are in 4 places, you're using sp3s. In the trigonal bipyramidal family, you're using sp3d, and in the, whatever this is called, octahedral, you're using sp3d2. You have these on one of the sheets that I gave you. You can figure them out every time after you draw the Lewis structure, because they're just adding up everything here to make the same number of orbitals that you had here, you're just giving them a different name. Or you can memorize them. So let's do an example. We're going to predict the geometry and then the hybridization for the central atom, that means the middle atom. First we're going to do SO3 2-, which is the sulfite ion, not the sulfate ion. So first we have to draw the Lewis structure. So for sulfur, I have 6 valence electrons. Each oxygen has 6. 3 times 6 is 18. And then I have 2 extra. So that gives me a total of 26 electrons to play with here. I'm going to put my sulfur in the middle. You know what I should do? 1 second. So we'll put our sulfur in the middle. Put 3 oxygens around it. I'm going to give it a lone pair. But I probably shouldn't do that. And then I will, so first of all, 1, 2, 2, 4, 6, 8. Something's going to be funky here. Okay, so we'll try this. So I have 6. electrons, 12, 18, 20, 22, 24, 26. However, so I'm still going to put my sulfur in the middle, and I'll put 3 oxygens around it, but I don't like the fact that I had that +1 on my sulfur. So I'm going to move one of my electrons here to make a double bond. I'm still going to keep my lone pair here. So now my sulfur, which has 6 valence electrons, is assigned 1, 2, 3, 4, 5, 6, and so it has a formal charge of 0. I'm going to put these here, but only that 2 pairs there because oxygen could only have 8. Now I'm going to count 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So this is a better structure because the formal charge on my sulfur is 0, the formal charge on this oxygen is 0, and the formal charge on the other 2 oxygens remain -1 and -1, but this is an ion, so I do need a charge of -2. So this structure is better than this one because I have more zeros here. Okay, there's less charge floating around, canceling each other out. Okay, so the geometry of this one, we have 4 electron domains, so the geometry for this will be in the tetrahedral family, and it's going to be trigonal pyramidal, right? That's what we call it. Trigonal pyramidal. It's in the tetrahedral family. Pyramidal. You should check that on your sheet. I may be remembering this trigonal word incorrectly, but basically it's a tetrahedral that's missing, that just has a lone pair in one place. We're going to come back and talk about the hybridization for this in a minute. So I want you to write it on your paper. We will come back and talk about how these bonds are hybridization. It's in the tetrahedral family, so we should have sp, each one of these should be an sp3 bond, but we have a double bond here, so we need to talk about what's that doing. So hold on to this thought. We're going to go to the next slide and do SF6. So for SF6, I'm going to put my S in the middle, and I'm going to, S has 6 electrons. I have 6 fluorides. Each one has 7, so that's 42. So I have a total of 48 electrons. There's not much I can do here. I'm going to put 6 fluorides around this. And then each one gets 6 electrons. And this is going to give me my structure. All my formal charges will be 0 because my sulfur is assigned 6 electrons, and it has 6 valence electrons. Fluorine has 7 valence electrons. It's assigned 7. So this is my structure. My geometry is an octahedral. My hybridization. For hybridization, we're going to look around our central atom. This sulfur was, it had S, P, P, P. This is its basic state. It's, in order to bond, it's going to promote 2 of these electrons into d orbitals. So then it's going to have S, 3 P's, and it's going to use 2 D's, which gives it a possibility of 1, 2, 3, 4, 5, 6 bonds, but they all have to be the same. We can't have 3 different kinds, and S types, P types, and D types. So we're going to combine the names of these, and we're going to call our 6 babies now, S, P3, because there were 3 P's, D2, because there are 2 D's, and we'll have 6 of these, which is a lot to write. 1, 2, 3, 4, 5, 6, and each one is S, P3, D2, each one is da-da-da-da-da, and each one of these will have 2 electrons. No. Take that back. It would let me erase. Each one will have 1 electron, and when they bond, each one will get one of fluorine's electrons here that will overlap. The black electrons are coming from fluorine. That's overlapping its p orbital with this sp3d2. So the hybridization here is sp3d2. The shape is octahedral. Now we're going to go back, we're going to go forward, but we're going to talk about that double bond that was in the SO sulfite ion. So there are at least two types of bond theories. The one we've been talking about is valence bond theory, where valence electrons in their orbitals essentially overlap and form a bond because each orbital contributes 1 electron and they're shared. There are 2 ways, then there's another type of bonding theory called molecular bonding, which we're really not going to talk too much about in this class. There are 2 ways orbitals can overlap to form bonds between atoms. They can just overlap. We looked at this slide earlier. Hydrogen had an s orbital, chlorine had a p. They overlap, and they each bring 1 to the table. If we were to draw this in a Lewis structure, you'd see hydrogen here, chlorine would be here, and they're sharing these electrons as they overlap. It's head-to-head overlap. Select cylindrical symmetry of electron density about the internuclear axis. Whatever that means. No, I'm just kidding. It means something. But the electrons are shared in between the 2 atoms. Not necessarily equally, because chlorine is much more electronegativity, but they're shared in between. So now pi bonds are going to be how we describe double bonds. Like we saw our double bond in our sulfite ion. When we drew it earlier, we had 1 double bond. So this pi bond is going to be characterized by electron density above and below the internuclear axis. So if right here we have the sulfur nucleus and this is the oxygen nucleus, the pi bond is occurring above and below where these are. Whereas the sigma bond, which is the regular single bond, is the sigma bond, that's occurring in between. So now we're going to talk about pi bonds and look at some pictures. So when we have a single bond, we have 1 sigma bond. That's what we call it. A single bond is 1 sigma bond where the electrons are in between the 2 nuclei. And the symbol for sigma is this funny little thing. When we have a double bond, we have 1 sigma bond and we have 1 pi bond. Pi, just like you write it in math, pi. And when a pi bond, if we say this is the nucleus and this is the nucleus, you'd have the electrons, the sigma bonds would be buzzing around in here. But your pi bond, which I'll do in a different color, the electrons are going to be shared above and below. In a triple bond, you have 1 sigma bond and you have 2 of these pi bonds. This would be an example where you'd have 1 sigma plus 2 pi. Here are some more pictures. So this is C2H2. And this carbon, this is a linear arrangement around geometry on each of these carbons. This carbon has formed an sp bond, 2 sp bonds, and this one has formed 2 sp bonds, and they're overlapping. So their geometry is linear. Now remember, carbon has, if we were to draw the Lewis structure for this C2H2, it's going to look like this, I think. Make sure I have enough electrons here. I might be leaving 2 out. 2, 4, 6, 8, and I should have 10, I think, right? So there has to be a triple bond here. That's the Lewis structure. So the one that is this bond right here, this single bond, this sp bond, comes from the one I'm going to draw in red right now. So in this case, and so sp hybridization implies a linear geometry. So carbon had 2 s electrons and 2 p electrons. In this case, it promoted its s electron, so it had 4 electrons capable of bonding, but the ones that are making this bond are these that I'm circling in blue. So we made two possible baby bonds here from the S and the P, so that we have an sp here and an sp here. They each contain 1 electron. This one contains 1 electron, this one contains 1 electron, this one contains 1 electron. And then so here, these 2 overlap to make a bond. This one overlaps with the hydrogen, this one overlaps with the hydrogen. Well, what happened to these electrons over here? They're going to form 2 double bonds. So this electron here from one carbon is going to combine with another p electron from the second carbon, because there are 2 carbons, and they're going to be shared above to make a double bond. I'll draw the other electron. So let's just, this is 1 electron configuration after the carbon has contributed these to these 2, each of it to its 2 bonds. The other carbon, we'll draw in black, would be sp, sp, pp. It also has an electron here, an electron here, and those are gonna, this one's gonna combine with this one, these 2 will combine with hydrogens. Here, so, yeah, I'll change colors, green. So these electrons that I'm going to circle in green are going to form this double bond, 1 double bond. We'll mark it here in green, up here. And in purple, these remaining p electrons are going to form this triple bond. I'm going to mark it in purple up here. Down here, it's in purple. Actually, did I do that incorrectly? I don't think so. So we have a pi bond and a pi bond and a sigma bond between these carbon atoms. So not all of your electrons have to go to single bonds. The ones that go to pi bonds don't necessarily affect the geometry. It's they're above and below. So I'm going to end this video here, and we will pick this up next time. We'll talk a little bit more about pi bonds and a little bit more about the energy of bonding, tying this back into thermochemistry.